Good morning, good morning, grade 11s. So today we will be dealing with a very important topic that I thought it's important that I should share with you. So in front of you, I've decided to put an A4 piece of paper like this one, a glass of water, and you'll see that you also have a pencil on your desks. So with these observations that I've made, there's something that I would like you to do on that A4 piece of paper. So you can see that on your desk, I've decided to arrange you so that you are in groups of 5, and we are going to perform this very same experiment that I'm going to show you today, and you also write your observations on the paper. So with the A4 piece of paper, you're going to draw arrows that are pointing in the same direction like this one. And once you are done with that, I would like you to put the A4 piece of paper behind the glass filled with water like this, and make sure that your glass is clean and clear. Don't worry about this one. This is just a stand so that you can all clearly see in class. No one is distracted from seeing the view. With this A4 piece of paper, you can see that these arrows are pointing in the same direction. So what I would like you then to do is to lower the piece of paper such that the bottom arrow is behind the glass filled with water, and the top arrow is above the glass filled with water. So please look at this. Something is happening there. I don't know if you can all see that. Can you see that here the arrows are facing in the same direction, but the moment you put the arrow behind the glass filled with water, what you are seeing on your side is that the bottom arrow is now facing in the other direction. So I would like you to try and think of what is exactly happening with that, because I'm failing to understand as a teacher. However, with the help of you guys, I'm hoping that you're going to come up with much very better explanations than I thought of. So make sure you have that piece of paper drawn like this one, arrows facing in the same direction, and make sure you help your peers in the group so that you can all see what is happening. So you perform the same experiment. Secondly, this is a pencil. Mine is green. I don't know what color is yours, but this is a pencil. And what I would like you to do as well with the pencil is to put the pencil inside the water and see what happens in the pencil. So what I see from my side is that when I put this pencil inside the water, it looks like it's bent to me. Whereas when I take it out, it's not bent, but when I put it inside the water, it's bent. So can you also try to explain to me what is happening with this pencil? Because I'm failing to understand. Why? Because if I put it straight like this, it does not seem like it's bent to me. But the moment I put it at an angle, it's bent. Then please guys, do this experiment as well and try to come up with the explanations and write down the observations that you made. Maybe there are some things that I've left out in these observations, but from my observations is what I see, and I'd also like you to write down your observations, and once you have those observations, you'll try and explain them, and as we are going through the lesson. And now that you have performed the experiment, there are a few questions that I would like to ask you. And the first one is, what observation did you make when you submerged the pencil inside the water? And what observation did you also make when you were putting the arrow behind the glass filled with water? Did you make the very same observations with me? If you remember, I had these two arrows, and I also hope you also had the two arrows. What observations did you make as well? And can you please maybe try to scientifically explain to me what is happening there? Because as I have told you, I'm trying, as I'm doing my own research, to understand and figure out what is happening in those experiments. And now that you have also performed the experiments, can you also try to explain to me what exactly is happening? There's some information that I've tried to gather together in order to try and explain these observations, and I'm hoping that they make sense to you. So, ladies and gentlemen, it came by surprise to me that this whole concept revolves around the concept or the topic known as geometrical optics. And geometrical optics really is just a topic that looks at how light really operates, because what we see today is because of light. So let me just take you through some of my findings. Prior knowledge. So the first thing that you need to know before looking at geometrical optics is that light is important because it gives us information about the world around us. I mean, come to think of it, you wouldn't be able to know where you are going or where you are coming from if it was just dark. So you really need light in order for you to have information of what is around you, or what you want to touch and want to feel. So really light is very important. So what you also need to know, or what you should already have known, is that light travels in a straight line. So from that beam of light with many rays of light, I would just like you to just focus on just one of them in order for us to simplify things when we are looking at geometrical optics. And the other thing that you also need to know is that light, the speed of light in a vacuum or in a space that is not filled with air, it's just 3 times 10 to the positive 8 meters per second. So when light enters our eyes, we see things in one of two ways. So you can either see light directly from the source, which is just from the sun or the light bulb, or what you are seeing is just what is reflected on you, because some of the light can be shined on the object, and then the object absorbs that light, and then some of it is reflected back to the person that is observing that particular object. Let me just try and show you what exactly I'm talking about here. You can see that this person on the left is looking directly at the light bulb. So what is happening there, as I've mentioned, is that we see light in one of two ways. This person is looking directly at the source, which is the light bulb in this case. So this person is looking at the light directly from its source. Whereas the person on your right, you can see that this person is looking at an object. But then how would this person be able to see that he's holding this particular object is through a reflection? The other question, let me just also show you. You can see on this picture that when I talk of reflection, is what I mean exactly is that you can see that there's a sun there. That sun directs sunlight or sun rays to the object when you're looking at the tree, to the object, which is the tree in this case. So what the tree does, it absorbs some of this light for its particular uses, like photosynthesis, as you may have learned maybe in life sciences. And then some of that light is not all absorbed into the tree. Some of it is reflected back to the observer's eye. So what you are seeing when you're looking at the tree, you are not looking at the source directly, you are looking at the tree, the object, and then how then able to see that that is a tree. It's because of the light that is reflected upon from it to your eye in particular. So then you can already see that through light traveling in a straight line from one medium to another, the speed must also change, because some of it, as I've told you in that tree, is absorbed, some of it is reflected back into your eyes, and also if the light ray strikes the medium at an angle, the change in speed causes the light to bend at a boundary between the two medium. And if you can think back into like that experiment that we have performed of that pencil, you remember that pencil, when you put it straight inside that water, it did not look like it's bent. It just looked maybe enlarged if you observed that. But then if you put it at an angle, you can see that when the light is approaching the pencil at an angle, some of it is bent. How is it bent? At the boundary of the water and air. Remember, there's two mediums there. There's air, which is above the water, and then inside the water, it's water. So at the boundary there, where the light strikes the object, you can see that it's bent. So what is happening there? It's one of the reasons why you saw that pencil bent in that experiment. So really what we're talking about today is just the reflection of light and the refraction of light. And please take note, these two terms are different. Reflection is something else and refraction is something else. So when I start talking about reflection, what I mean here is that when the light is hit at the barrier of a particular object, it bounces off. It just hits at the barrier of the object and bounces off. And what the law of reflection says is that the angle of incidence, which is a new term that I'm going to explain to you now, the angle of incidence is equal to the angle of reflection when you're talking of the law of reflection. So please take note of that law, because you are going to need it at some of the questions that you are going to look at as you are going along. So there is it exactly. On this object, imagine this being the mirror. I'm sure you've already seen this. When you're shining light on the mirror, most of that light is reflected back. Maybe, I don't know where, maybe if you're inside the room, you can see it at the ceiling board or at the roof when you're reflecting light on the mirror. So what is happening there, you have that thing called the normal. And really what a normal is just a perpendicular line that is perpendicular to the cross-sectional area of that particular object. So you can see there we have a normal, and then the angle, this is the angle at which the sun ray is approaching this mirror. Remember, there's beams of light or rays of light approaching this object, but for simplicity purposes, we just took one of those, as I mentioned at the beginning of this lesson. And you can see that the incident ray there, it hits the sun, the mirror at an angle, and the angle between the normal and the ray is what we call the incident angle. And the incidence angle is related to the incident ray, because the incoming ray is what we term as the incident ray, and the reflected ray is that one, and this is the angle of reflection. So when we are saying the angle of incidence and the angle of reflection are equal, this is what we mean. So please make sure you keep that law in mind, because the law of reflection, you will need it in some of the future questions that you are going to deal with. So without any further ado, this is what I would like you to try and figure out. You can feel free to pause the video and try to label the incident ray, the angle of incidence, the angle of reflection, and the reflected ray, and the normal. Once then you are able to do that, you can go forward with the presentation. Now I'm going to touch on refraction. So refraction is the bending of light when it travels from one material into another, in which it has different velocity. Remember, I told you that light travels at different speeds in different mediums. Just like in water, it travels at a speed that is different from air. So this is what is refraction is looking at. So you can see here is an example. Here we have a normal, just like we had before, and this is the boundary between air and the glass filled with water. We can say it's filled with water, or it's just an empty glass. Either way, they are different. So there we have air, here we have glass with water. So what is happening when you the angle of incidence is that one, between there is the normal and this is the refracted in this case. Remember, we're talking about a refraction. So what I want you to notice then is that here we have glass with water, here we have air. So what is happening here, air has a particular refractive index, of which the topic that I'm going to tell you just now, but just keep in mind that air has a refractive index and glass also has its own refractive index. But what I want you to notice is that air has a refractive index that is lower than the refractive index of water or glass. So what is happening is that in that case, you are going to have the incident ray bigger than the refracted ray. Why? Because the refractive index in here is bigger than the refractive index here. So the speed at which light is traveling through this medium is going to decrease. And when the speed decreases, the angle between the normal and the refracted ray is going to be smaller as well. But then once the light comes out of this medium back to air, what's going to happen, the speed is going to then increase from point C to D. The speed is going to increase. And please make sure that you notice that the AP is kind of parallel to CD, even though they are not in the straight line, but they are parallel, if you can maybe take that into consideration as well. But this angle here is going to be the same as that angle there, whereas this one is going to be the same as that one there. So that's what is happening there. And remember, when I put that pencil straight through the water, there was no bending of the pencil happening, or the observation rather. This is because now the incident ray is just passing through like this, even though the speed is decreasing, but there's not going to be any refracted ray there, and then hence why you are not seeing bending of that pencil when you put it straight inside the water. So now, when you talk of refractive index, what we are talking about here is that the ratio of the speed of light in a vacuum to the speed of light in another medium. So it's just looking at the ratio between the two, because remember I said the speed at which light is traveling in a vacuum is different from the speed at which light is traveling in water. So what the refractive index is looking at the difference between those two and giving you a particular value that you are going to work with. And please make sure you have that formula as well, which is just N is the refractive index, C is the speed of light in a vacuum, which is just 3 times 10 to the positive 8, and the refractive index, the dimensionless number, or what we are saying there, it's unitless. It does not have any units. It's just a ratio. A ratio does not have any units. And then that small letter V there is just the speed of light in that particular medium. So with that information then, I would like you to use the following table to answer the following questions. On your right hand side of the table, you have the refractive index, and on the left hand side, you have different mediums. Here you have diamond, you have glass, you have benzene, and you have water. So the first question that I would like you to answer is to maybe, or rather try to find the speed of light in diamond. So you can see the temperatures are the same. They have decided to keep them the same. So diamond there, I want you to find the speed of light in diamond. Remember in the previous slide, I showed you that formula. So you must be able to answer this question easily because you already have the refractive index. You already have the speed of light in air, so it must be easy for you to find the speed of light in diamond. You also try to find the speed of light in water and try to compare the two, because you can already see that the refractive index of diamond is bigger than the refractive index of water. Then when you're looking at the speed, please try to compare the two and then maybe try to come up with an explanation of what exactly is happening there. Please feel free to pause the video, work through the question, and when we are done, continue. I'll provide the answers at the end of the session. Lastly, a very important topic, Snell's law. So what Snell's law is dealing with, it's the law of refraction. When you are talking of Snell's law, you are talking of refraction. But there are other topics that we are going to also deal with as we go further with the topic. We are going to look at total internal reflection. We are going to look at the angle of critical angle. Those are the topics that we're going to deal with in future. But then now, before we even go there, I want you to understand Snell's law. And Snell's law is also dealing with the same topic that we have also dealt with, which is the refraction. Refraction also touched at the refractive index. So what really that is that when you are looking at that this formula rather, you can see that you have the refractive index, So now there is this subscript at the bottom of each refractive index. So what this really means is that this is the refractive index of the medium containing the incident ray. So if your light is coming from air to water, the refractive index of water is going to be this one, because that's where the incident ray is. That's where the light is coming from into water. Then there's going to be the refractive index of water, because that's where the refracted ray is going to be. If you can still recall that diagram I've shown you of the incident ray, a refractive ray, and the angle of refraction, the angle of incidence, then that's what you're going to use. It's going to be the angle between the normal and the refracted ray. This is the angle between the incident ray and the normal. So with that information, please use the table I've shown you in practice question number 2 to answer these questions. So with these questions, really what you are going to use is just Snell's law, this one. Please use this formula to answer these questions. And the first question says, if a light ray is traveling from air into glass, while the angle of incident is 30. So you already know that it's from air, that's going to be the incident, into glass, that's going to be the refracted. So the angle of incident is between the normal of air. Remember the boundary between air and the glass, that's going to be the incident ray that's coming through air into the glass, and the angle between the normal and the incident ray is this one. So what we are looking at, we are saying find this angle here. They've given you this angle, they are saying find that angle. So surely, since the refractive index of air is smaller than the refractive index of glass, you must have a smaller refractive index, which then means your answer should be less than 30. And if it's greater than 30, you must know that there's somewhere where you went wrong. And then at the end, the second question is saying, draw a diagram showing the path of light ray as it travels from air into glass. I think I've already shown you that one. And with these particular answers, I would like us to mark them before we end today's lesson. Grade 11s, now that we have went through these very important topics, I hope everything makes sense. And now what I would like you to do is to, on your way out, when you move out of the classroom, take that piece of paper that I've prepared there. It's the homework for you to do at home, so that for those of you who did not really understand the concept, you can go through the homework with the help of others. And when you come back and meet for the second lesson, we will continue.